Now, rather than talking about just a point charge and what a particular charge has to do in the effect on other charges, more commonly what we set up is what's called an electric field. An electric field is just by external means, such as magnets or various other things. We can set up an electric field so that, for instance, the electric field always goes this way, okay? So this is the negative side, this is the positive side. And if we put a charged particle in there, and if this is more negative over here, more positive over here, and we put a positive charge in here, it's gonna want to stay over here. But if we put a negative charge in here, it's gonna be attracted over to the positive side, and it's gonna be pushed away from the negative side. So an electric field, if we have a uniform electric field everywhere, instead of having to do this calculation, whereas if we were talking about two charges, and they are passing by each other, or this was passing by that one, not directly toward it, well then we have to deal with the vector aspect of that. But if it's a uniform electric field, we don't have to deal with that. And so in the case where we have a uniform electric field, it turns out that that potential that we have, that electric potential, which we just got done saying, well, that electric potential that we got, the potential energy that we got, was based on Q, E, and the distance that we traveled. Well, if the electric field is given to us as just some constant, we don't have to worry about what that electric field is precisely, then we look at this and say, well, it matters how far we push this thing, how far we've moved this thing, and then the charge that it has. So that's the electric potential. So we can think of that, the distance traveled there. And we also have another number that we talk about, or another quantity that we talk about, and that is, instead of just the potential energy, we talk about the potential difference. The potential difference is just this piece of that. It just has to do with the electric field multiplied by the distance that our particle is traveling. That gives us the electric potential, the distance that our particle wants to travel. So, for instance, we have the positive charge here, and we look at what this voltage is across here and how far that charge is going to move, and that would tell us what the potential difference is between those two sides. That's what the delta V is. And if we look at, again, relating all of these things, well, force was these, but if we remember, total force was all Q1, Q2, we had this K, and over R squared. Well, as we go progressively from force, well then E is that with just one of the Q's, because Q times E is force, so if we just divide through by Q, we just get this. And if we go the additional step of saying, okay, we have E, we have some distance that we're traveling here, so E would be KQ over R squared, and then we're multiplying times the distance. Well, if that distance is the same as this distance right here, which when we're talking about the distance between this particle and where the electric field is, etc., they would be the same. Those would cancel, and what we end up with for potential difference is KQ just over R. Now, I mentioned in class very briefly before that there is a quantity called an electron volt, and that, you know, a single 1 coulomb of charge is 1.6 times 10 to the minus 19 joules, which obviously is a very small amount. And when we're talking about individual charges, it's usually beneficial to talk about something that's not 10 to the minus 19, something of that order. So the unit of an electron volt is defined. Usually that's just written like this. And that is the kinetic energy that an electron gains when accelerated through a potential difference of 1 volt. So with what we were talking about here, okay, if we flip this around, we say, okay, we put a negative charge over here, what's going to happen to it? It's going to be pushed, oops, we put a positive charge over here, we put negative charge over here, what's gonna happen? It's gonna be pushed that way, okay? If it's pushed that way, and if the difference here is 1 volt, and that electron, how hard it is then pushed, the amount of kinetic energy that gets, or the amount of work that's done that it is pushed with, that is 1 electron volt, because it's an electron being moved by 1 volt of electricity. And it turns out that 1 electron volt is equal to this 1.6 times 10 to the minus 19 joules. So that's a conversion that we can use, and frequently it would be more convenient for us to talk in terms of electron volts than in terms of joules in these cases, because the amounts of energy we're talking about are so small.